This is part 4 of the series Similarity, and we're going to begin this part by putting into practice the side-side-side similarity theorem. So here we have three triangles, and we want to determine which of these triangles, if any, are similar by side-side-side similarity. Now, we don't have any similarity statements to go by, so what we're going to do is we're going to use the largest side of these triangles to determine which ones correspond to which. So here we have OC and IL. So let's go ahead and start writing down these ratios. We have 21 is to 12. 21 is to 12. As the next biggest is 15 to 10. 15 to 10 and 12 to 8. So if we cross multiply these, 10 times 21 is 210, and 12 times 15 is 180. They do not match, so these two triangles are not in proportion because these two sides are not proportional to these two. So let's go ahead and try this triangle and this triangle. So we'll take the biggest here and the biggest here. 21 is to 14, as 15 is to 10. Again, we have 210 equals 210. So let's use the third ratio. We have 12 to 8. 12 to 8. Let's cross multiply these. 15 times 8 is 120, and 10 times 12 is 120. So since all these sides are in proportion, these two triangles are similar. So let's go ahead and write a similarity statement for these two. And what we're going to do is we're going to start from this vertex and go across the smallest to the biggest, which means we're going to go smallest to biggest. So it's going to be DOC, so we'll say triangle DOC is similar to triangle. Again, we're going smallest across biggest, JAK. Triangle JAK. Now this similarity statement, of course, is extremely important because it has to identify the corresponding vertices and therefore identify the corresponding side lengths. So DO corresponds to JA, and OC, the longest side, corresponds to AK, the longest side, and then DC, the middle side, corresponds to JK, which is the middle side. So those two triangles are similar. Now let's compare doing it with just comparing the ratios. 21 divided by 12 is 1.75. If we look at 15 divided by 10, we get 1.5. And we can see again, just like we showed here, these two sides are not in proportion, so these triangles can't be proportional. Likewise here, we could say 21 divided by 14 is 1.5, and 15 divided by 10 is 1.5, and 12 divided by 8 is also 1.5. So we can see that all of these ratios are the same. These sides are in proportion. Now as the last check, let's go ahead and look at these two triangles. And we can see that the largest is 12 and the largest is 14. But we have here, the middle is 10, and the middle is 10, the smallest is 8, and the smallest is 8. So clearly, these two sides aren't going to be in the same ratio as these two. This is 1 to 1. This is 1 to 1. 10 divided by 10 is 1. 8 divided by 8 is 1. But 12 divided by 14 is definitely not 1. So these two triangles aren't going to be similar. Let's move on to another kind of example. In this example, we want to determine what value of x would make these two triangles similar. So they're giving us a potential similarity statement. ABC similar to DEF. So we're going to use this potential similarity statement to match up our corresponding side lengths. Now it almost doesn't really matter where we put these things. This is going to be kind of a tricky thing to work with. So BC corresponds to EF. So these are two corresponding sides and they both have variables. So we're going to have to do a little algebra here. Let's get started. And we're going to start with BC. So we're going to say x plus 1 is to EF 2x minus 3 as, go back to this triangle, we use AB, 9 is to AB corresponds to DE, which is 12. So we used our similarity statement to say BC corresponds to EF and AB corresponds to DE, and we create our proportion. Now we're going to go ahead and try to manipulate this algebraically and see what we come up with. So we're going to multiply 12 by this. So we have 12x plus 12 equals, and then we're going to multiply this by that. Basically, we're cross multiplying here. Ordinarily, we don't want to just do that blanketly, but we don't really have a choice here because we have to get this x term out of the denominator, and that means multiplying both sides by this whole expression, 2x minus 3. So 2x times 9 is 18x, and negative 3 times 9 is negative 27. I'm going to collect my x terms on the right hand side here. So we're going to subtract 12x. So 12 equals 6x minus 27. We're going to go ahead and add 27. So that's 39 equals 6x. Finally, we'll divide by 6, and 6.5 equals x. So the value of x that makes these things proportional is 6.5. And if we wanted to add that in there, this side length becomes 6.5 plus 1, which is 7.5. And this side becomes 2 times 6.5 minus 3, which is 10. And so 7.5 divided by 10, 7.5 divided by 10 is 0.75. 9 divided by 12 is going to be equal to 0.75. And lastly, 12 divided by 16 is 0.75. So we can see that all these three sides are in the same ratio, three pairs of sides in the same ratio. The sides are corresponding and proportional. Therefore, by side-side-side similarity, these two triangles are similar. And let's move on to the next topic now. Now we come to our third triangle similarity theorem, and that is the side-angle-side similarity theorem. If two side lengths of one triangle are proportional to two side lengths of a second triangle, and the included angles are congruent, then the triangles are similar. Again, this should not be confused with the side-angle-side congruence theorem, because we are talking about proportionality related to these sides and not to congruence of sides. The included angles are congruent, but the sides that include those angles have to be proportional. So that's the idea behind side-angle-side similarity. Let's go ahead and see if we can put this theorem into practice. Here we have an interesting example, and we're going to try and show that LIM is similar to triangle ALM. So triangle LIM similar to triangle ALM. So to use side angle side similarity, we have a side, we have an angle, and a side. And again, we have a side, an angle, and a side. So since we know that these two are right angles, this is a linear pair, and it's a congruent linear pair because they're both right angles. Therefore, we're going to have to use this side, and this side, and this side, and that side. So let's go ahead and start writing our relationships and see if our corresponding sides are proportional. So I'm going to start out with IM. IM is here, and I'm going to write 18 is 2. IM corresponds to LM. LM is 24. So just to try and avoid confusion, we had IM on this triangle here corresponds to IM corresponds to LM in this triangle. This side is not being part of this one. So it's this side in this triangle, 24. Now, let's go back to our first triangle, and the only other side we have is this one, but it's now LM as it relates to triangle LIM. So LM, 24. LM corresponds to AM in the other triangle. AM is this side. So 32. Now we can do either the equality of cross products or we can do the ratios. So this ratio simplifies to 3/4, and this ratio also simplifies to 3/4. If we want to do cross products, 18 times 32 is 576, and 24 times 24, 576. So no matter how you slice it, these two sides are proportional, and so we know that the corresponding side lengths are proportional and the included angles are congruent. Therefore, by side angle side similarity, triangle LIM is similar to triangle ALM. Let's move on to the next section where we're going to look at some theorems that give us proportional relationships, but not necessarily always with triangles.